Okay, we are live. Hello everyone, and thank you for joining today. I, Arnav Vora from IIT Bombay, representing the Indian Youth Water Network, welcome you all to our second talk series lecture. Today's talk would be delivered by Dr. Veena Srinivasan on the topic Understanding the Interplay Between Data and Models in Water Resources Research. Before we begin, I would like to thank viewers who registered prior to the talk with questions for Dr. Srinivasan. We shall be having a question and answer session at the end of the talk where the same shall be discussed. As we proceed, if you have any questions, please use the Google form in the video's description to send us your questions. A link to the form has also been shared with registered viewers. Our volunteers Sai Veena from IIT Bombay and Rashmi Kulranjan from A3 are monitoring the responses. Questions asked during the talk shall be addressed at the end in the Q&A session. We are delighted to have Dr. Veena Srinivasan, the director of A3 Center for Social and Environment Innovation, for our talk today. Dr. Srinivasan has a track record of formulating and guiding major interdisciplinary research, innovation, and capacity building projects in the area of climate change and water, water security, and citizen science. She has won several awards for her research, including the 2015 Jim Doog Award for Best Paper in the journal Hydrology and Earth System Sciences from the European Geophysical Union, and the 2012 Resources Research Editor's Choice Award from the American Geophysical Union. She has also been the chairholder of the prestigious Prince Claus Chair in Netherlands from 2018 to 2020. Thank you for joining us today, Dr. Srinivasan. And without further ado, I would like to welcome you to the talk. Over to you.
Thanks. Thanks so much, Anav, for that wonderful introduction. And it's really a pleasure to speak to the audience today. I'm super excited about the Indian Youth Water Network, and it's a real pleasure to be able to speak to and hopefully interact with such a dedicated bunch of people. So let me start right away with my talk. So I'm going to talk a little bit about understanding the interplay between data and models and water resources research. And the reason I thought this was an interesting topic was because of the way we think about data and models in water resources research, particularly, and I'm focusing more on the natural science part of water resources research as well as interdisciplinary research. So mainly quantitative approaches. And the reason I think this is very interesting is because I think the way we do it is unique to water resources. It's even different from the way ecologists do ecological modeling or even any of the other allied environmental sciences. And I think, therefore, that some of the challenges and also I think some of the blind spots emerge from this. So I'm going to basically start by laying out how we approach research in the field of water resources. So typically what we might do is we'll ask questions, and the questions that we ask are often based on what models we are comfortable using. So if we use SWOT, we are often asking questions that we know that SWOT can answer. If we are using WIC, then similarly. And so we typically have a set of models, our pet models that we feel comfortable with, and the research questions that we ask are based on that method. And then we build models, depending on which model we prefer, but it's typically based on what data we actually have access to. And in fact, I would say that go one step ahead and say the choice of models itself is often based on what data we know we can get. And then finally, if we are inclined to make, do any kind of future scenario modeling or make policy recommendations or just, decision support of any kind, then they are based on what the models are capable of projecting. Right? Because we are constrained by the world, the modeling world in which we inhabit. So the question I want to ask today is basically, and this is my message for the talk. So if you want to fall asleep at this point, this is really the message that you want to take away. The message I want to give you today is that can we switch this by instead of asking questions that we know our favorite models can answer, can we learn to prioritize questions that will actually impact decisions on the ground? Second, instead of building models that we based on the data that we have, can we instead think of data collection as a separate process that enhances process understanding and also can be used to validate secondary data? And finally, instead of making recommendations based on what models can project, Can we instead craft model scenarios that answer contemporary debates in the water sector? So, what I'm going to do is for each of these three recommendations that I'm going to make, I'm going to give you an example of how I approached this switch, the switch from what I would call a more conventional approach to approach that I favor in different pieces of research. And I want to therefore warn you that these are actually three separate talks and three completely different, at three different scales and three completely different case studies. So the first question is, can we switch from asking questions based on what our models can answer to prioritizing questions that would actually change decisions on the ground? Now, what are the differences in the types of questions that we might encounter in these two situations? So for instance, if we're asking questions that a model might answer, it might be, how will stream flow change if temperature and rainfall changes, or how will stream flow change if land use changes, or what will happen to the inflow of a dam if we implement certain types of interventions, or what would happen to a flood peak under urbanization, or if we build an embankment, or so have you. And the reason often that these questions are valid questions to ask is because these are questions that can be answered that by the types of models and methodologies that we use. Now, and the problem is that often when you deal a lot with stakeholders on the ground, and I talk to a number of government agencies, we work with other NGOs who work on the ground. We recently started working with a number of donor agencies, as well as funders who fund in the water sector. And the kind of questions they ask you are completely different. So they will ask you, for example, in which kinds of watersheds should I invest in if I want to rejuvenate water bodies? Should I do that? Can I do it anywhere? Or are there certain characteristics of the watershed where that will give me the biggest bang for my buck in the sense of having the maximum impact on groundwater levels or farmer incomes or whatever? Or a government agency may say, if I ban eucalyptus in this district, will it bring up groundwater levels? Or Central Groundwater Board or a Zilla Parishad may ask, well, how do I draw the aquifer boundary? And this is in particularly in hard rock systems, which is it's hard to do, where I know that if I implement a certain set of interventions, it's not going to create leakage outside of that boundary, right? I'm able to isolate and manage a particular geographical area separately. Now, these are very different types of questions. And the problem that we face often is that because we are so comfortable with the methods and models that we use, often the questions that we are able to answer are limited to what the models can answer. And so therefore, what will it take for us to completely flip it around and ask a very, very different set of questions? So the first case study is the work that we've been doing in Upper Arkavati, and a number of my PhD students are continuing this work. It's not over. But basically, we started off many years ago by asking the question, of what was causing declines in into the TGLE dam. I'll just go back and show you here. The TGLE dam, it's about a 1,500 square kilometer catchment, and this is the single dam. Now, one thing about these watersheds, which are common throughout South India, is that these are cascading tank watersheds, which means that the watershed is not completely hydrologically connected. Instead, the water runoff generated in any given sub-catchment will run off into that tank. And only if that tank fills up will the water get into the next catchment and next catchment and next catchment. So if you look at this big tank here, which is Hesarghatta tank, Hesarghatta tank hasn't overflowed since 1992. Right? And so you have to ask the question, if I had a time series starting from 1995 to 2020, it's a 25-year time series, is it even meaningful for me to consider this entire catchment as the catchment of the TGLE reservoir when not a drop of water has actually crossed this point? Right? So then I would argue that realistically, it's only this piece. And yet, if we did this blindly, we would just delineate the catchment and then kind of say, here's what I'm observing at TGLE catchment, and then do some model that we are comfortable with. But it doesn't make sense if there's no water that's crossed Hesarghatta. We know that nothing that's happening here, you could have like 25 dams happening there and nothing is going to impact a drop of water here because no water has crossed this point in the last 25 years. So when we started asking this question again, like I said, there's almost a 90% decline in the period that we studied it, and it's changing now for various other reasons, but from 1940 to 2010, a very, very severe decline in stream flow. And when we looked at that and we looked at climate change, the obvious answer is people will say, well, what's happening with climate change. Unfortunately, when we started looking at the climate projections for this part of India consistently show increases in rainfall and not decreases in rainfall. So, how do you explain a decreasing historical trend when all of your models are going to basically suggest that rainfall is increasing? And that then immediately tells you, well, if it's not climate change, there's only one of two possibilities. For some reason, the models have got it wrong, right? And the climate models are saying it's going to increase when in fact there's been a declining trend. Or there are other reasons which have nothing to do with climate change, which are contributing to declines, right? And so when you started asking this question, we had to we had to then explore this question. We couldn't just blindly say we'll take a model, throw climate in there, do a bunch of climate projections and expect that it's going to explain the non-stationarity. That's not going to work clearly. Now, I wanted to make the point that this has real world implications, because often whether something is caused by climate change or caused by anthropogenic drivers shifts the burden of responsibility on whose job it is to then remedy that and what kinds of interventions can remedy that onto different agencies. And if you were a state water resources agency, it would be very reasonable to say, look, why don't you just show us that? Why don't you, if you said it was climate change, it would be so much easier for us, because then we could go and justify a bunch of interbasin transfers. But if you start saying pesky things like it has to do with groundwater depletion or something else, then we've got to do a whole bunch of other interventions to fix that. So you could certainly imagine that there would be a certain a certain group of people that would feel much more relieved if you showed that it was climate change. And so this is it is an academic question, and it's an interesting academic question, but it's an academic question which has real world implications. So the way we set up about doing this, and we initially set this up by asking what we would call, I would say, just back of the envelope calculations, right? Basically saying, let's just quickly check of every possible hypothesis that can drive drive decline in stream flow, and can we kind of then do order of magnitude calculation. So all we are doing here is order of magnitude calculation. We know how much the decline in stream flow has been, and then can we kind of look at the order of magnitude calculations for various different hypotheses, and then kind of say which ones are plausible and not, right? And so we said, well, maybe it was rainfall that decreased, maybe it was temperature increase, maybe it was groundwater pumping that reduced base flows into streams, maybe it was increased evapotranspiration, because we knew from our recce visits that eucalyptus plantations had increased very substantially in the catchment. And then maybe it was what people were saying, that it was stream flow fragmentation, which is what we were calling the million puddle theory, saying instead of the water all coming into these tanks, for some reason, the catchment has gotten so fragmented that the water peak stopped here and there, and then it's just evaporating. So we call that the million puddle theory. So the first one was it rainfall? And we did not find any significant decline in rainfall. Naturally, I'm just showing you the annual rainfall, but we looked at rainfall intensity, looking at the various percentiles of rainfall, the number of rainy days, and so on and so forth. And there were not any significant statistical declines in the rain gauges that we had continuous time series records for. For this part of the catchment, I want to say that it's not true completely for all parts of even the Kaveri Basin, and certainly not for all parts of India. The second thing is, could we see a rise in temperature? And so we didn't have, every kind of data. We would have ideally liked all of the weather station data, full data set of all the weather station parameters. We only had max and min temperature, but and so therefore we were able to use the Hargreaves equation, which is, got its own limitations, but there wasn't a significant increase in the potential evapotranspiration, right? And so if it doesn't show a significant decline, we couldn't then say that we can explain a 90% decline in stream flow based on temperature either. The next one was groundwater pumping. And here, again, our initial back of the envelope showed that the annual season crop report for the district, and this is publicly available data, right? It showed two things. Firstly, that surface water had disappeared and groundwater had taken over since starting the late 80s, the mid 80s. And then starting the early to mid 90s, open wells had disappeared and bore wells had taken over. And this kind of told us that, okay, clearly there is, surface water has disappeared and shallow wells have disappeared. And if shallow wells have disappeared, there's chances are that base flow has declined as well. And so then the next thing we did is we said, okay, can we do a base flow index calculation? And indeed, using a standard base flow recession approach, you're able to show that the base flow index goes down. But the other interesting thing, which I just like to show for fun here, right? Before we even did the base flow index, all I did was to say, can I say how many months in a year that there was rainfall, but no stream flow? And you can see, I didn't expect to see anything. I mean, this is just a random thing, right? Why would you expect? But the result is so dramatic that not a single year after 1992 was there rainfall, but no was there no rainfall, but there was stream flow. And so you only had, after 1992, you only had stream flow in months when it actually rained, right? And so this, like I said, only because it's so dramatic, the pre mid 90s and the post mid 90s, and that same number of the mid 90s comes up, if you remember, in our previous graph, which tells you that that's exactly when the open wells all went dry, which suggests that the mid 90s probably is a period when the shallow aquifer dried up. And that indeed shows up when we look at well histories and a whole bunch of other data. If somebody's interested, I can show you those other pieces of data, but it shows up in many, many, many different ways, which then again allows you to triangulate and say, okay, this is a story that's plausible, that mid 90s was when the shallow aquifer dried up and base flow probably disappeared. The fourth hypothesis was eucalyptus plantations, and we did, basic land use land cover analysis and found a fairly substantial increase in eucalyptus plantations. So again, back of the envelope, let's look at how much the evapotranspiration from a ragi crop versus eucalyptus would be, and that's quite a substantial amount. So if the eucalyptus is not moisture limited, then it's going to be able to take up quite a substantial amount of water just because of the nature of eucalyptus. And that does tell you that it's plausible that eucalyptus could be a significant factor. And then the last one was streamflow fragmentation. So we looked at all the check dams. We knew the check dam density from having done very, very detailed field surveys and kind of done check dam censuses, and we know the size of them and so on. And so we could say, what's the maximum amount they could have evaporated? If all the water went into check dams and just evaporated, what's the maximum that could be? And it wasn't a large enough number for us to say that check dams alone, right, could have caused it. Now, later we'll see, and in fact, Lakshmikant, who's my PhD student, is looking at a whole bunch of other variables, which is not the stream interventions, but looking at the aerial interventions like like farm bunds, for example. And those then show very different orders of magnitude. Those actually can explain a decline in stream flow, but check dams alone can't. So the long and short of it is that it couldn't have been climatic factors that could have explained this massive decline. It had to be anthropogenic factors that were plausible. Now, of course, the next step of it is to actually figure out all of those processes and then be able to build a model to include all of the anthropogenic interventions and then show that all of that rainfall which happened is now being compensated by increased evapotranspiration or increased bare soil evaporation, either through plants or other forms of evaporation. But the point is that you have to then be able to explain where all that water is disappearing, and that's kind of the work that Lakshmikant is still doing. But I'll show you two pieces of work which show you that in terms of being able to start to tease some of these factors and say, okay, how do I start building a model now that I'm talking about a catchment which has got a whole bunch of anthropogenic interventions and I don't know which processes matter, right? So for example, if we wanted to have an independent estimate of whether overland flow is an important mechanism or not, this was work that was done by Gopal Penny, who was a PhD student who worked on this catchment with us. He was then at the University of California at Berkeley. And what Gopal did was basically he sat around in the stream, often in the middle of the night, but basically through a storm, he collected samples from three places. He collected rainwater, he collected soil samples, and then he collected stream water, right, over the period. And this is an elapsed period. And he did it for two different storms. The red is storm A and the blue is storm B. So two different storms, both in the middle of the night, because in Bangalore, it mostly rains at night. He sat in the middle of these streams and then he collected these samples from three places. Now, P, the circles are precipitation. The triangles are stream flow, and S, the squares, are soil moisture. And what Gopal was trying to do is to say, does the water that's in the stream, that means do the triangles, look more like the circles or more like the squares, right? So now, for the moment, look only at the red ones, because that is one storm, right? And I think that it's quite obvious that all the, the circles and triangles are here and the squares are down here. So for storm A, the stream flow looks much more like precipitation and doesn't look anything like soil moisture at all, which tells you that very little of the rain is being contributed, as base flow. Most of it is actually direct runoff, overland flow. And then the same thing for the blue storm, which is storm B, right? And basically, you're just looking at the deuterium concentrations and saying which ones have similar signatures, and that is allowing you to build a hypothesis for saying what might have been the dominant process which might have contributed to it. So Gopal's entire thesis was based on basically trying to figure out which processes dominate. Now, the second one he did, and I'll walk you through this, is basically he wanted to know, is of the overland flow mechanisms, is it infiltration excess? Okay, and for those who aren't familiar with this term, infiltration excess is when it rains, it is the rate at the intensity of the rainfall greater than the saturated hydraulic conductivity of the soil. That means, can the soil take it fast enough? Or if the rainfall intensity is so much that it's just the soil can't take it and it's going to run off, that's called infiltration excess runoff. Or is it saturation excess? That means that the soil is already so soaked up with water that the rain has no place for it. And that's the reason you're getting runoff generation. So all of these then determine which equations go into your model later. And therefore, it becomes really important to know which of the dominant mechanisms are. So we know that overland flow dominates, very little base flow. And then between overland flow, we wanted to know, is there any significant evidence that saturation excess plays a role, or is it all infiltration excess? And the answer is it's mostly infiltration excess. How do we know that? Because you can see that this is the rainfall. This is the inflow into the tank, both of these. So we had a rain gauge, and then we had a stage measurement in the tank, the local tank. And then we had soil moisture sensors at multiple depths in a couple of different fields. We had one which was a grape field and one which was a ragi field. Now, the main thing is, if it was saturation excess, and you can see this is the soil saturation going from 0.2 to 100. Now, the point is that if it was saturation excess, you should have seen the topsoil being saturated before runoff was generated and not the other way around, right? But you're actually seeing in both of these cases, and he had multiple such events, and therefore you could see it in all of them, that your soil was not saturated before the rain event, then it rained, and then after that, you're seeing the soil being saturated. So clearly it tells you that the runoff didn't, and the runoff had already occurred by then, right? You can see where the peak runoff. So the runoff occurred not because the soil was saturated, but the runoff occurred because the intensity of the rainfall was greater than what the soil could absorb. And this then tells you that what kinds of equations and you can feel comfortable with. It basically helps you define model structure, right? So this is the reason we go down this path. Now, as a simple, to end the first piece of it, of my talk, which is why you should ask research questions that matter, and not just those that your favorite model can answer. Now, the second piece of it is, I'm going to suggest that you want to build models. You don't want to just build models based on the data you have. You actually want to collect field data to improve process understanding, or you might even want to use it to validate secondary data. So if you were doing it if the entire purpose of field work was just to collect data to validate your favorite model, or calibrate your favorite model, calibrate and validate your favorite model, then you would say, well, I want to collect groundwater levels, I need reservoir data, I need land use land cover change, I need pump test data, whatever. So all of the stuff that feeds into your model. But if you were actually doing it to understand and improve field understanding, then you would ask very different questions. You would say, why are there discrepancies between monitoring data and where farmers are distressed? What's driving that? Or you'd say, what patterns do we see in inflows and in reservoirs, and why is this not making sense? Or you would say, what does the groundwater level even mean? Or what does the surface water level even mean? Very, very different set of questions. And it's important to do that. Personally, I feel, and I really wish that everybody listening to this talk would go and seriously start looking at data, because it's really fascinating what you can learn when you look at the data for its own sake, instead of looking at data as just something I blindly feed into a model, right? So I'm going to give you the case of the Mettur Dam and some work we did on Mettur Dam. Mettur is the first dam in the Kaveri Basin. As soon as you cross the border from Karnataka to Tamil Nadu, that's where Mettur is, and that's where all of your Kaveri tribunal disputes are all about the transfer from KRS to Mettur. I mean, that's what the entire story is about. So of course, clearly it matters. How much water you have in Mettur is important. Lots of people care about it. Now, the first thing that we look at is when you just look at the meters above mean sea level, there's a strange kind of thing of why does the minimum reservoir level appear to have increased over time. And this was a question actually that our collaborators at British Geological Survey asked us, saying, are they managing it differently? What's happening? Why do you see this weird kind of thing at the bottom? And then so when we did some little bit of digging, the newspaper said Mettur Dam has been silted quite a bit, and you were seeing numbers of like 30% in the newspapers. And I had actually visited Mettur Dam during the 2016 drought, and I saw that it was almost completely dry at that point. So I knew that the dam was pretty severely silted, both based on newspaper reports as well as my having seen it, right? Now, then we looked at what did CWC has done, these siltation studies in Mettur Reservoir. What do the siltation studies in Mettur Reservoir say? So what they tell you is that the gross storage of the reservoir, right? This is, everybody knows that you have a gross storage, which is your total storage, and then your live storage is above your sill. That means, above your, so really the dead storage is really what you have to account for siltation, right? So this was the original gross storage. And then the total storage by 1978 had gone down from 2,700 million cubic meters to 2,200 million cubic meters. And then by 2004, it was only 1994 million cubic meters. This is from Central Water Commission's own siltation studies, right? So just want you to keep that 1994 as the maximum storage of Mettur Reservoir at the back of your head. Now, when we look at, just plot the Mettur data, right? This is from whether you do India Varis or whether you do PWD. This happens to be PWD because India Varis only has the most recent data, but this was PWD data. When you actually go to the dam, they've published it, so you can literally manually transcribe it, and that's how this data was arrived at. They only have 2 data points a year, so they don't have the entire series, but it's for the biannual series, biannual data. And what you find is that this is what the gross storage of Mettur was in 1934 when the reservoir was constructed, and then these are the levels which CWC has come down. But what you can see is that the reported levels in Mettur Reservoir are actually exceeding what CWC itself says is the maximum reservoir of Mettur, right? So there's an issue here, and what that tells you is perhaps they haven't controlled or they haven't corrected for the changing bathymetry of Mettur Reservoir. So what did we do? We said, well, let's just test that hypothesis. All we do is draw the stage storage relationship, and you see this is right from 1934. And what you see is that even when we use all the data, the stage volume relationship has remained totally constant, which means that they are not updating the bathymetry of reservoirs. And this is true of most reservoirs, right, in India. So then we said, well, how do we, of course, that immediately raises a problem. Don't blindly use reservoir storage and assume it's correct. And if you're off by 30%, there might be a very good reason why you're off by 30%. But we asked the question, what can we do about it? And this was work done by Pranuti from my lab. And what Pranuti did was she looked at just Google Earth imagery. She looked at a number of data sets, but this is Google Earth imagery. And she noted what the stage was reported for that day and what the area was for that day, right? And she kept doing this over different stages. And when you do this, you can actually get the area based on what you can actually see from the satellite imagery from a cloud-free image, and then the stage on that date, on the image date, right? And then you can get an area, stage area relationship. And you can also then, based on that, develop the contour of the reservoir, just based on those different images and reconstructing it over time. And then if you have a stage area relationship, a stage area relationship is saying basically that for any given height, this is the surface area that is being exposed, right? So what I can do is I can literally add them up and integrate them, right? So the integral of the stage area relationship gives you the stage volume relationship. It's just basic calculus, nothing, no rocket science there. And indeed, if you look at the satellite imagery and reconstruct it, you can actually see that 30% decrease that is being reported between what CWC says and what we are actually reporting is actually 30% less. And so that actually is confirmed by CWC's data. What this tells you is in this case, we actually had CWC data, which we could check against. But if you had satellite imagery, you could in fact use this method to reconstruct reservoir bathymetry elsewhere. But it also tells you, for Christ's sake, don't use data blindly. I mean, actually use and check whether this data makes sense, because there are issues with data. Just because the data is there, it doesn't mean that you have to use it. So I think that I can give you lots and lots of different examples of where there is data where there are clearly issues, not because people are doing the data wrong. There's no dishonesty or any of that in this argument, right? But what it's telling you is that the data always doesn't mean what you think it means. So ask the question, does this data mean what I think it means? Okay, so my third piece of the talk today is to make recommendations, to not make recommendations based on what models can project, but rather model scenarios that are interesting and reference contemporary debates in the sector. So again, let me kind of walk you through those two and how you might do things very differently. So if you were making recommendations based on what models can project, you would say, how do I know how, if I change dam operation rules, how that would affect stream flow, or how that would affect canal allocation to different canal command areas? Or I may say, if land use change, what would it affect on land use? So if I was afforesting or deforesting, if I did a clearance of a wattle or precipice or whatever, how is that going to change stream flow? Or I might say, what would happen to groundwater depletion if I changed my under different scenarios of climate change, or if I priced electricity, or I did something, or I had a interbasin recharge. Those are things that I can do with models. We are comfortable with that. Now, often the problem with taking that approach is, unfortunately, what policies get recommended or what policies even get debated are driven by what our models that we are comfortable with can ask. Instead of saying, how do I build a model that would ask these really interesting questions, most of the time you're saying, I have this model, this is what the model can do, and therefore these are the questions I'm going to ask. But instead, for example, some of the big questions that come up in contemporary policy debates is, should we go big or go small, right? Should I build more dams? Should I do watershed development? Should I have a desalination plant? Should I do rainwater harvesting? Or we might say, okay, under what circumstances do different solutions work? So if I do check dams, do they work anywhere the same way, or do they work differently in different places? Or if I did solar irrigation, we're having a talk through IWWN in a couple of weeks on that. If I did solar irrigation, does it work everywhere, or are there different constraints in different places? So, what are the unintended consequences? When do they happen? These are the kinds of questions that are being asked in the policy debates. These are not necessarily, and to be fair, I'm painting with a very, very unfair and broad brush here, but these are not necessarily the questions that we ask because of our levels of comfort. So I'm going to tell, and I think this is really important, because what we are then allowing to happen is we are saying the models that we are comfortable with are going to determine our water future for the country. And that makes me very uncomfortable, because then we are basically saying that it's really allowing the tail to wag the dog, instead of really asking, what do we really want to do, and how do we know which are the good, better options and worse options? We're basically flipping the entire thing around. That makes me uncomfortable. So I'm going to give you a quick, and this is these papers are all out, so you can go and read most of these. You can go and read up. But basically, this is based on my own thesis research, where I studied the 2003-2004 Chennai water crisis. And during that period, which happened again last year, but during that period, the city's reservoirs had dried up, the pipe supply system shut down. The vast majority of the private bore wells in the city went dry. And then this is how the city looked. The entire city was supplied by tankers. And so when I started my research, I started asking the question based on a policy debate that was there, which is, what do we do? How do we avoid such crises, and how do we fix it? And I found that there were very different solutions that were being recommended by different stakeholders. So Chennai Metropolitan Water Supply and Sewerage Board was saying, let's build desalination plants. And that's and Veena and so on. That's the supply augmentation option. Though the development banks will typically say, wait a minute. Firstly, you're giving water away free, which is insane. Secondly, you have a 50% leakage, and that is also crazy. So why don't you fix your efficiency issues first, and then you can go and build interbasin transfers, right? And that's a typical example, a typical position that economists would take. And then the environmental NGOs and Center for Science and Environment had just won the Stockholm Water Prize in 2004, where for basically making the case for urban rainwater harvesting, saying what you've essentially done in these cities is you kind of lost your entire access to rainwater because you paved the whole city over with no recharge. And so if you compensated for that paving by mandating rooftop rainwater harvesting, you'd allow the city's aquifers to fill up, and therefore there would be a backstop so that people's wells would not go dry, and they would at least have this backstop thing, and you wouldn't have this issue of everybody having to buy tanker water if your hand pumps and your open wells still contained water. So the problem is that this is not the type of policy debate that you could actually address with the kinds of models we have, because they're completely different fields. One is talking about groundwater, one is talking about consumer behavior, and one is talking about desalination plants. How do we even start to bring those together to basically even say, is one better than the other? And as a result, if you don't say, is one better than the other, often what you get is what I call the kitchen sink problem, where they'll say, let's just do everything. And let's just do everything often is, let's do the expensive, horrible stuff, and then let's do this little time pass stuff that you guys want, right? And so it's really difficult to say, if I did rainwater harvesting, can you avoid building that desalination plant? That is the kind of question that you can't answer. And it's a really important question because you're talking about a difference of some 10,000 crores often, right? So this was a research question that I asked, which is what contributed to the water crisis? And then I asked, well, which of those different policies would be affected in preventing such a crisis in the future? Of course, nobody listened to me 10 years later. That's a different story. So the thing is, the way we conceive of these models is what I would call a centralized paradigm, right? You have a water utility, it gets water from well fields and from reservoirs, and then the utility supplies it through a pipe supply system to consumers, and consumers have overhead tanks because it's an intermittent supply system and so on. But the problem is this doesn't really describe what happens in cities, in most cities in India. Firstly, we know that the most cities have intermittent supply systems, which means that you're not getting pressurized supply to the taps. You're really delivering the water to a sump, and then from the sump it's going to an overhead tank. And then a lot of households, the richer ones, have bore wells, and then they're supplementing with that. And so you have a fairly substantial amount of groundwater, and then you have tankers as well. And this is true of every city in India. And in Chennai, what we found is that between the drought and the wet, it varied, but between 25 to a quarter to two-thirds of the water was coming from these non-utility sources, which means that how are you even able to describe what is happening in a city if you don't even have the ability to conceptualize it as a complete system? And so what we did is we said, we're going to conceptualize it as a complete system. We're going to say, all of these things feed in. The consumers get water from multiple sources, and they all go to the consumer. And then I'm going to actually, because I'm asking policy questions, I need to be able to look at the quantity that's actually coming to the consumer and then be able to translate that to a rupee value. I don't have time in today's talk to get into the entire economic model that we use, but it's important to say that for this model to work, it was really important for us to spend a ton of time on imagining that consumer model, which in today's language you call an agent-based model, which is not a language that we had at the time. But basically, I needed to understand how the agent switches between multiple sources, and only if I have that, I'm able to then be able to pull the whole system. So then I can ask questions like, what caused the crisis? And of course, this is what, when you put the whole model together, what it tells you is, firstly, Chennai didn't have. Now this is an older piece of work. It didn't have enough reservoir capacity, and it still doesn't. And so when you have a multi-year drought, the reservoir system goes down, exactly as happened last year. And when the reservoir system goes down, you don't have enough water to put into a pipe supply system. And so you fall below the pipe supply threshold. And therefore, the entire system basically is 0 day. You get a 0 day situation where the supply ends, and then you only have tanker supply. Then everybody, of course, turns on their wells and starts pumping. And so the second thing that happens is it's important to note that when pipe supply shuts down in cities, again, true of all cities in India, because you have so much pipeline leakage in cities almost contributes to half of the total recharge. And so, two things happen when pipe supply shuts down, when 0 day happens in cities. One is your recharge goes down by half, and then, of course, everybody's turning on their bore wells 24/7. And so, the number of wells in the city that go dry increases greatly. And this was based on both household surveys as well as validated by the model. And then you get a tanker market. And then again, in my model, because I have an agent model, I can kind of say how many people have become tanker dependent, and then what's the size of the market that's going to throw up. And we actually did measure the size of the market. So in Chennai, at least, all of the tankers came from outside the city. So you could actually stand at all the major highways coming into the city, and the number of tankers that you counted. And I literally had field assistants do that, count every tanker that came in over a 24-hour period. And that literally tells you the size of the tanker market. And then you're able to validate that against a model. So every piece of this is validated against field data, right? And then, like I said, because I was using an agent model which actually measured consumer well-being in economic terms, I can then do cost benefit and say what was the loss. I can quantify a loss in consumer well-being, right, between the wet and the dry year. And then you can do this into the future. Now, the important thing is what it allows you when you have this kind of integrated model is it allows you to ask these questions, because it can say, what happens when you raise tariffs? What happens when you reduce pipeline loss leakage? What happens when you increase recharge, and so on? And so I can do that. I can change all of those things in the model, and I can run it again. And I'm not going to bore you with the entire result, but you can basically see for every time I can basically check between what the baseline is saying and what my policy scenario is saying. And basically, it's telling me that under this policy, there's a lot fewer wells going dry, right? My baseline had a lot of wells going dry. And then in a future drought, simulated future drought, and then currently a lot fewer wells going dry. And then similarly, I can check what's the size of a tanker market, and then what's going to happen with the differences in consumer well-being. And this allows me to then come up with a cost benefit and say, should you do this or should you do that, right? So I know that this was very, very complicated, because it is complicated. I just wanted to walk you through a case study which would allow you to see that it is possible to flip the question around and start with a policy question, and then be creative and build a model that in a robust and defensible way will allow you to answer that policy question. And in this particular case, it was very complicated because we had a pipe supply, and we had aquifers, and we had tanker market, we had consumers, and all kinds of crazy stuff. But I think the thing is, at least it started off with what is my policy question and how do I build a model to answer that, instead of the other way saying, which is the model I feel comfortable with and what can I answer with that. So the long and short of it is, this is the summary of my entire talk today, which is, firstly, I'm making a three-part argument. First, I would really, really recommend a shift to prioritizing questions for which the answers really matter. We need that. India has enough of a severity of a groundwater crisis and a water crisis that we really need answers. And when I speak to NGOs on the ground, when I speak to donor agencies, like, I feel 80% of the questions they are asking, we don't have answers to. And so the only way that we are going to get there is if every single one of you starts answering those questions. And I really hope that the India Youth Water Network will be a forum to be able to answer those questions. The second is collect field data, but not just here's the data I need to calibrate a model, but really collect the field data and look at the data in and of itself and say, what is the data telling me? Is it telling me stuff that I didn't know? Is it telling me something interesting? Am I getting new process understanding by looking at it? So really collect data to test and improve process understanding. It may be to test specific hypotheses, like the ones I showed you for the overland flow and the infiltration excess versus saturated flow. But it could be a whole bunch of things. In the Chennai model, we tested it to basically say, how do consumers behave? All kinds of things were but the data sets were actually, each one of those modules was underpinned by a massive data set. And then test it like we did in the Metur case to validate secondary data and say, always do a smell test saying, does this data make sense? Do I believe it? If I don't, why don't I believe it? And always look for discrepancies. If your data is telling you something which your field experience is not, it's really a, it's really important to interrogate and say, why is there this discrepancy? So some of the other work we did, for example, um, on our survivor bias groundwater level work came from that, right? Because the monitoring well data was telling us something, our field experience was telling us something different, and we really said, how do we kind of breach this gap? And the last piece of it is that the purpose of simulation models is to extend data, and it's not meant to be sacrosanct. And so your model is basically, first you've got process understanding from the data, and then you're using that model to basically say, how do I extend it into situations which don't exist at the moment? And when you do that, you want to constantly make sure that you're interrogating both model structure as well as data, right? And you can see one of the things we did with this, as well as other, both the Arkavati as well as the Chennai work. We basically asked a lot of questions about model structure, and then of course really look about at human feedbacks. I'm not asking everyone to build a full social hydrology model with a two directional feedback as the Chennai work did, but to really ask whether human interventions are changing some of your assumptions or processes as you understood it traditionally. I'm going to end with this, which is a plea, which is, I know that there is a temptation for so many of us, because we don't have resources, we don't have money, to say, I wish I could study river system somewhere else because the data is complete. But I would say, ask interesting questions. And I was one of the reasons I included the Metur study is because a lot of that data was based completely, it didn't involve field work, right? It involved looking at satellite imagery and painstakingly trying to interrogate secondary data sets. And at least that is always possible, even if you don't have budget for field work. So I'll end with this plea, but I really look forward to the discussion and any questions you may have. Thank you so much for attending and listening.
Thank you for the truly insightful talk. We have 10 questions coming from our viewers who registered previously as well as during the talk. And I'm going to go through all of them one by one. We'll start with the first one. It comes from Ekta from Central University of Gujarat. And the question is, what would be the most important factor to consider while making a conservation plan for the peninsular rivers of India?
Great question, Ekta. So I think it's a tricky one to say what would be the most important factor to consider, because one thing to realize is that there are multiple stakeholders who have very different objectives for what they think they want the river to look like, right? And so the thing is that it's not that every stakeholder has a single vision. So this is what, at least in our A3 parlance, we often call normative concern. That means different stakeholders care about different things. And therefore, you can't come up with a conservation plan unless you're clear. And you may choose to ignore some stakeholders, because some stakeholders may say, I want, water parks in the middle and I want to pave everything and have whatever, right? Dancing monkeys in it. I mean, and people can say crazy stuff. So you do need to, but you do need to listen to what visions people have for what their end goals are. And then you need to have a way of saying, okay, these are the set of stakeholder or goals that we want to meet. Then you need to be able to translate those into actual water quality and quantity numerical numbers. And then you can kind of say, build a model, look at scenarios and say, what will it take for me to achieve the water quality and quantity goals that we have arrived at, which were arrived by consulting stakeholders, and what objectives they looked at, right? So I know, I don't know if you were looking for a specific look at groundwater, look at this, look at that, but broadly, you there's a set of parameters that you want to arrive at. But you first, the tricky part, the engineering and the hydrological modeling is the easier part. Getting to stakeholder consensus, that's the harder part. I hope that helps. How do we do model efficiency in data scarce mountainous environments? You know, I think that it's not an easy question, because if you have, the problem we have in a lot of Indian models is that they are poorly constrained, right? You have too many parameters, too many degrees of freedom, and too little data to be able to be able to constrain the models. Personally, I would be very happy if people took a step back from modeling in data scarce environments and tried to first increase data density. So there's been some excellent work by Atree's team today. In fact, several of our colleagues are in Meghalaya, for example, in actually installing various kinds of flow sensors. But I really think the interesting questions in mountainous environments are not from modeling, but actually come from field data collection, because we don't understand what drives spring flow, to what extent do different types of vegetation and their evapotranspiration, potential evapotranspiration patterns change seasonal spring flow. I mean, there's a whole bunch of basic fundamental questions that we haven't answered. So if I may, I would, and it doesn't answer your question at all, because there's no easy way to improve model efficiency when you don't have data. It's just, but my challenge to you would be to say, can you improve your data density in simple ways? And the thing that I will say is, field data collection is becoming cheaper and cheaper. And there's a lot of increasing interest in it. And I would just see even crowdsourced data. I mean, there's a whole bunch of other types of data and that you could use. But I would say increase data density first, instead of trying to improve model efficiency without doing that. And if you aren't able to at all do it, then I would see if you can use the kind of approach we used in Arkavati, which is first getting your back of the envelope calculations correct, making sure that you know which your most sensitive parameters are, and then kind of focusing on your efforts a little more. Okay, next. What role does qualitative data play in the process of data collection and analysis? I mean, great question, Meghna. I'm going to, I mean, qualitative data is super important. There's lots of reasons you want to do qualitative data for its own sake, right? For qualitative data, because you want to understand narratives, you want to understand, why people think the way they do, what drives them, what makes them, what drives their perceptions of different things, a whole bunch of reasons. But let me focus the answer on how qualitative data influences quantitative models, because I think that's a more specific answer. There are several ways in which you can use qualitative data. So, for example, one of the things that, based on what the first Ekta's question, right, which is how do you come up with a conservation plan? And I said that, well, you need to know what stakeholder priorities are. So one of the important ways in which you come up with you use qualitative data is by actually constructing those stakeholder narratives to say which futures should I be modeling, which futures should I be examining. And so if you look at the entire literature on narrative construction, often narrative construction is what feeds model construction, right? And so I think that is one really important thing. Rashmi, who's here, who's my PhD student, is doing some very interesting work looking at social media analysis, trying to answer the question of, what research questions, or where are the gaps, or what research questions do different stakeholders find interesting? Where are they struggling, and what are the questions that come up over and over again? She's asking this in various different ways, but it's a way that she's looking at very specific user groups and their analysis and analyzing social media data using NVivo, which is a qualitative analysis software. So again, that doesn't necessarily feed into a model, but it's something that could inform both science, in the sense of, if you want to ask what are the really interesting questions, or you want to ask the question, how do I develop model scenarios, then you can say, well, what is it that my stakeholders care about? So number of different ways in which you can do that. Another way that qualitative data is often used is in, if you wanted to, for example, build a model and you wanted to come up with rules of operation of different infrastructure projects, right? And if you look at in a quantitative model, you actually do need to say, well, it's turned on, and if the level is above, reservoir level is above this, then only this sluice is turned on or that sluice is turned off. I mean, there's a whole bunch of complicated things that go into how infrastructure is managed. And most of the times when we model it, we kind of assume that the rule curve is just followed. But actually, if you went and did a bunch of interviews with people, you would find that the rule curve is deviated from all the time, and the way infrastructure is operated is completely different from what anyone thought about. So another way that you could use it is to use the interviews to say, can I actually backtrack and figure out what rules people are using for operation of this infrastructure? So I mean, I can go on and on. I don't want to bore people forever, but there's lots of different ways in which qualitative data feed quantitative analysis, and that is completely separate from qualitative data for its own sake, which is a whole rich area of study by itself. Next. Is it possible to create water resources models that account for indigenous knowledge systems and practices in the field of water supply and sanitation? So the combination of water resources models and water supply and sanitation is slightly throwing me off, because water supply and sanitation, the way I think of it, is much more a delivery oriented field, saying, it's very consumer focused. While water resources, we are more talking about, groundwater models and surface water models and so on. But there's certainly ways in which indigenous systems and practices can be accounted for. I'll give you a couple of examples. One is, some of the ways in which we're looking at how, so Aquadam, let me use Aquadam's example. Aquadam is a very, very well-known NGO. I don't know if all of you are very familiar with them. Please go and look them up. They have something called the barefoot hydrology practice, where what their entire, groundwater management solution is based on training people, as well as allowing them to use to map aquifers based on their indigenous understanding of the system. And often people have very, very intimate understanding of ground and surface water flows, for example, and then being able to use that to actually map the aquifer in a structured way, right? So it's a basically integration of science with what people already know about their watershed. I mean, so that's one example. That's an excellent way. I mean, there's lots of different ways in which you can use it. People use it for, suppose you're talking about ecological flows, right? And you want to know what is, there's an endangered species, let's say something like the gharial or something like that. And you want to understand what causes the populations to expand and contract. And you can't go back into history and get data, because you just can't, right? I mean, we don't have a time machine. So what you do, one of the ways you can do it is you can ask villagers, and there are ways that you do it carefully and well, and triangulate across different insights across different people and so on. But there are ways to ask people and say, what happened in this year, what happened in that year, when the water level was here, did you see this, these kinds of things? And then you're able to kind of come up with a very simple relationship between the species of interest and the water quality and quantity. And I'm making stuff up like this, but there are ways in which this is done very elegantly, where indigenous knowledge is used to reconstruct river health indices, to map different systems, map springs, all of this stuff. Hope that helps. Next question. How do we collect data accurately in the field? So there's different types of data, right, that we collect. There's data and there's data. There is data which is sensor based, which is and it can be low cost, it can be high cost, and of course, if you're using sensors, then you want to make sure you're calibrating them. You want to keep you want to make sure that you're updating your calibration. This is as true of if you're using research grade sensors that you've bought, because I promise you that once you put a sensor in the field, snakes will want to bite them, and they want to sit in the sensor box, and all kinds of stuff will happen. So you do want to make sure that you clean your sensors, you want to prevent fouling, you want to recalibrate them to make sure that there hasn't been drift, all of those things. And that's to do with the standard sensors, which is relatively easier than the other kind of the data that we talked about a minute or two ago, where the data is based on asking people, whether it's indigenous knowledge or whether it's survey data or so on. What we are finding increasingly is that the kind of tools we have today to be able to validate and ensure accuracy of data collection right in the field, whether it's Open Data Kit or whether it's Kobo Collect. I mean, there's a whole bunch of these smartphone-based data collection tools. They allow you to do all kinds of validation right in the field. For example, it'll tell you that if you're employing field assistants, if they are taking a picture of the let's say it's a manual stage device, they have to their GPS location has to register as being within 25 meters of the stage post, right? So there's all what we've been able to do very simply. By we, I mean the technological world has been able to do is be able to improve accuracy of data collection with modern field data collection tools by adding these kinds of checks and balances. And what I do with my own team, and we've been doing it very successfully, for example, is to do a lot of audio notes with Open Data Kit, so that when we come back and we've got little video clips and we've got photographs and we've got actual data and we've got audio notes, all of those are geotagged, and we are able to kind of then come back and as a team we are able to look at the entire week's field collection, kind of talk over what we saw in different places. It just improves the quality not just of the data collection but the quality of the interpretation and our ability to communicate within the team as well. And that is almost as important as the original data, because a lot of data gets collected and then nothing happens with it. It doesn't inform any insight. And so I think between all of these different tools that we have today, there's just so much. And all I can say is then triangulate, triangulate, triangulate. I mean, constantly question your data. Say, does it make sense? Does this match with that? Do things compare with each other? Do very, very simple analysis. I deliberately wanted to show you that very stupid base flow analysis that we did, which was such a simple indicator, but for me, very, very powerful. All right. Next question. Do you think setting up more real-time groundwater monitoring and stations have a role to play in urban India? Absolutely. Groundwater monitoring sensor costs have really come down. So, definitely there's all things that can be done. We are doing this as a citizen science project in Bangalore right now. We've been working with citizen groups with low-cost data collection, particularly on the water quality side, less on the groundwater side. But right now, my team is in the Delta, Kaveri Delta, installing low-cost groundwater sensors, and we have a citizen science project there as well, where we've given college teams salinity sensors so that they can develop salinity maps, for example. And we want to kind of see where saltwater intrusion is a problem, where it's not, all kinds of stuff. So I think, I think not enough can be said about the potential for these tools. I hope lots and lots of you are able to do it as part of your work. Hope that helps. Next. How do we approach modeling in a country like India, where data availability and authenticity is an issue? I hope that my talk today kind of gave you some sense of where we might be able to stretch data constraints and how you might be able to verify authenticity. There isn't a golden answer which is going to solve this in every situation, other than the question that I answered to the gentleman from Kashmir, that you want to increase data density when data availability is a problem. Authenticity, you constantly want to triangulate across data sets, right? Say that constantly ask the question, does this pass the smell test? And I feel we just don't do enough of that. There are like 200 PhD theses just sitting there. If people just looked at the validity of the data that's already in the public domain, and kind of try to understand that, there's that much work to be done. So I think constantly validating, triangulating, and improving data density. Next. How do you quantify the change in hydrologic parameters over the year through modeling? It's a tricky question. I'm So this is something that one of a master student who worked with me last year attempted, where, if you want to think about human interventions, a lot of human interventions are about, or they manifest as hydrologic parameter changes, right? For example, if you go to a catchment and put a bazillion check dams in, what you're essentially doing is making the catchment more porous, and therefore the infiltration characteristics of the catchment should change over time. I'm not a big fan of doing this blindly, where you blindly change it, though it's fun to do and kind of, see how do the parameters change in non-stationary, under non-stationary conditions, where you can't explain it, explain the changes just because of land use and climate, the standard forcing variables. But I feel that if you're going to do that, then you should be able to also collect field data and justify those parameter changes separately. Um, that's my recommendation, that you don't just say, okay, hydrologic parameters change every 5 years, fixing the model, because that becomes a bit of curve fitting, and I'm not a big fan of just brute forcing these things. So I would constantly say, can you justify that brute force changes? Because then otherwise, how do you know, you change that parameter, how do you know it's not that parameter and not one of 55 other parameters? Yeah. All right, next question. What's your perspective about the reasons we are looking for half hypothesis and answering them using a model, unlike the Arkavati example? Uh, One or two hypotheses and answering them, unlike the Arkavati where we looked at multiple ones. So yeah, I guess, I mean, in a sense that it's always a good example to look at many different, I mean, always a good idea to ask. But you're right, in a sense, I suppose it's the way we are trained, but I think it's also disciplinary bias, right? Because if you ask an economist, they will see that everything is explained by price. If you asked an anthropologist, everything is explained by culture. If you ask a groundwater person, everything is explained by, base flow, and so on and so forth. And so there is an issue of what blind spots we have, constraining the questions we ask. And I don't have a easy answer for, for it, other than to say, talk to friends. And that's really where I hope that you guys, as the India Youth Water Network, are able to just have conversations saying, why do I see this? And it's just lovely if people from different disciplines kind of look at the same data set and ask different questions, where you're forced to confront where your blind spots are. um, I hope that that ends up expanding people's frames more than they are at the moment. Can you say even domestic wells are being used so much that water should be metered? The recent state laws exempt them. Um, you're asking me a should question, which is hard to ask because that's, a should questions are always political questions, right? I mean, who am I to say? I can have a personal opinion, but who am I to say what is appropriate for the city as a whole? Um, as a general rule, I would say that it would be great for domestic wells to be metered. Um, it's hard to do because, you know, Bangalore's kind of had this law where you're supposed to declare if you're supposed to register your domestic well, right? How do you enforce something like that? And one of the biggest problems we have, particularly with respect to groundwater, is this asymmetry of information problem, where the people who have wells and are using the wells know how much they are using, but the city or the municipal authority or the water utility doesn't know. And if only I know how much I'm using, and there's no way for them to independently check. This is the difference between when they are delivering you the water, they know how much they're giving you because they can meter their own pipes, they own the infrastructure. With groundwater, it's your infrastructure and you're drawing the water. So it's very difficult for any third party to actually be able to overcome this asymmetry of information problem. There are ways that you can figure out how much domestic wells in the city are using, and one clever way to do it is to meter the sewage, right? Because you know how much is being supplied, you know how much is leaking roughly, and you know how much is coming back as sewage. So the difference must be groundwater based. But that only gives you the balance at the city level. It doesn't tell you who's using how much. Um, So to summarize that, I think it's interesting to know how much water domestic wells are using. I would love to see it being done. Technologically, there are challenges to actually enforcing it. It would be great. Sewage can't be metered. I mean, it's still too expensive. My understanding, maybe one of you guys will come up with a device and that'll solve that problem. But another interesting thing that we had been talking about for the last couple of years is this idea of net metering for domestic groundwater as well, saying that if you have rainwater harvest and you abstract and you show us the difference, we'll kind of give you some kind of credit for that, and that might then alter the incentives. Again, there's a whole bunch of technological tinkering which needs to be done because it's not like we've figured out the net metering problem for water. So yeah, I'll stop there. I think it's a great idea. I think there's a technology gap there. Comment from Aditi, who, yes, asked the right question. Is most of the work done? Yeah, I think. And then if you are, I think Aditi, it's half, not quite. I mean, it's definitely half. Because if you're not asking an interesting question, why did you spend all of that time doing it? I mean, I think for sure asking the right question is important. More mindful of this? What skill sets do we need to look at the problem in this? Now, they asked my PhD student, which means I'm being a terrible advisor here by not answering all these questions. Okay, what do we miss usually? What do we miss? And how do we be more mindful about it? Um, like I said, I think that everybody misses a different piece of it. So I don't think, and that's, as you said, a different it's there's not one universal answer. I think different disciplines have their own blinkers, about which part of the system we see. I think that first, talking to people from who look at it from a very different place helps. One thing that you guys might consider, which is to look at SYSYNC in the US, right? SESYNC, which was it's kind of socio-economic environmental synthesis center, something like that. And what they did is they created a program which allowed three PhD students in different parts of the country in different disciplines, and that's talking about the US, to come together and jointly look at a problem. That might be a nice structured way to think of it. If you can get somebody to fund it, maybe you guys can be clever and figure this out. That might be a way to kind of force people to work together, and then force people to kind of confront their blind spots. um, Failing that, I think an interesting skill set, one of the ways that we've been doing it, and this is now looking at CSEI, which is my innovation and impact center, which is not my research hat. One of the ways we've been doing this in a structured way is to do systems mapping, right? To say, can we map out the system? It only works though if you have enough interdisciplinary people in the team who are constantly kind of looking at it and saying, did we miss a link? So you really do need enough eyes on it, but doing systems mapping in a structured way, I think helps. Next.
Uh, yeah, so we're done with the questions. Thank you again for this truly, truly inspiring talk. And we also want to thank our viewers for joining today and asking some very interesting questions. Lastly, thanks also to our volunteers for helping organize this talk. And we shall be back again with another IYWN Talk Series lecture soon. Thank you, and bye everyone.
Thanks. Thank you.